Hello everyone, my name is Mark and my call sign is N9WIB. This is the Technician License Series, Lecture 11, and today we're going to cover basic antenna types. There are various different types of basic antennas in amateur radio. Probably the most common, and especially for people who first start out, is the dipole. And we will cover that, as well as ground plane vertical antennas. And then we'll go into calculating antenna length, review handheld radio antennas, and also go into directional antennas before we finish up. As I mentioned, dipoles are one of the most common amateur radio antennas, especially by people who are starting off in amateur radio. And they're probably one of the cheapest to make and homebrew yourself. You can purchase them online, but it's probably just as easy and convenient to actually make the antenna yourself with some basic stuff from the hardware. So what does dipole mean? So di means two. There are two poles to this antenna, or two wires. The dipole is a half wavelength long with quarter waves comprising each pole. So in total, that's total length. It's a half a wavelength long, and each pole of it is a quarter wavelength long. The dipole could be center fed, which is the most common, or you can actually create something called an off center fed dipole, or OCF dipole. In that case, the two poles of the dipole antenna are not the same. They're generally maybe one side is 2/3 of the wavelength and the other side is 1/3 approximately. And then you have to feed it at the point between the 2/3 and 1/3 length of the components. And one benefit of the off-center fed dipole is that you can actually have a multi-band antenna. Again, most dipole antennas are going to be horizontally polarized. You can have them straight, parallel to the ground, and hung up as high as possible. And you can also hang these antennas between trees or poles, or from your home and a garage or an outbuilding, or whatever you really need to do to get the antenna up to the appropriate height. Other dipoles consist of inverted V dipoles. So these are still dipoles, but instead of being perfectly parallel to the ground, the center feed point is going to be at the highest point and elevated as much as possible, while the two sides of the dipole are going to slope downwards and be draped diagonally to rest above ground level. You can put them at ground level, but then it becomes kind of a safety hazard with potential excess voltage coming off the end. So you want to probably fasten the two ends of the dipole well above normal human heights, maybe 10, 11 feet, someplace that's going to be safe and not in your way. The dipole radiation pattern is strongest broadside and weakest at the ends, meaning that at the very ends of the wires, at the very ends of the antenna, you're not going to be getting that much of a signal, but most of the signal is going to be perpendicular or 90 degrees to the horizontal axis. The radiation pattern can be said to represent kind of a donut on a string on each end. Okay, let's give you some examples of what dipoles look like. So we'll see if we can draw a few. So the standard dipole is going to have two ends. And it's going to be fed in the center. So this is going to be your coax or ladder line or whatever you use to feed the dipole. And this length between one end and the other is going to be half a wavelength long. And remember, the wavelength is represented by the symbol lambda. So that's your dipole. But each of these legs of the dipole, or components of the dipole, is a quarter wavelength in length. So you can use any type of wire. Usually, for my dipoles that I have at home, I'll use 12 gauge stranded copper wire that is insulated, that you can pick up at any home supply store, and that's relatively pretty cheap. So that's a standard dipole, and that it is horizontally fixed, and you can tie the ends off with some type of insulator and UV safe, non-conductive cord to a tree. Okay, I'm not the best artist. Or an outbuilding or some type of pole. And you want to get the dipole up as high as practical. So another type of dipole is the inverted V. So if you have a pole supporting it here, you can have the feed point in the center, and then the dipole slopes down with the diagonals, and these are equivalent to, again, quarter wavelength sides. But where you actually feed the dipole with the coax line is the center point, and that's the highest point. But you can have these each length go down and slope and attach to something a little bit lower on the ground. So the advantage of this is you're getting the center point as high as possible. But if you have a smaller structure that may be, let's say, a pole or a tree that's 12 feet off the ground, you can actually tie it off to that while getting the center point a little bit higher. And that's going to have a little bit of a different radiation pattern. And what else? Oh, the off-center fed dipole. So the off-center fed dipole is the same thing. It could be a sloper or a horizontal V, as we mentioned above. So this is the horizontal V. Or inverted V. It's the horizontal inverted V. So you're going to flip the V over and it looks like a V. But you have the off-center fed dipole here. And as you can tell, one end is going to be longer than the other. And the feed point is going to be maybe 1/3 the distance. And this is going to be 2/3 the distance. And your coax or ladder line is going to have to come off that point. One advantage of this is that it will act as a multi-band antenna. So if you have it long enough, you can go 80 meters, 40 meters and down and have access to a multi-band antenna and cut it to resonant frequencies and tune the rest with your antenna tuner. And we can see two radiation patterns for the dipole antenna here. One is the bird's eye view, or azimuthal, however you want to pronounce it. And you can see that it is more, it does radiate broadside and less so with the direct axis of the wire. And this is a horizontal view. You can see that there are two giant donuts along the parallel axis here, representing the dipole radiation pattern. And there's really not much at the end of the wires. Another type of antenna is called the ground plane. The most common ground planes are approximately 1/4 wavelength in vertical height. The feed point is at the base of the antenna, and it acts like a vertical half-wave dipole, but the other half is the ground plane itself. So only 1/4 wave of the antenna height is visible above ground, and the other half is called the ground plane. Now, the ground plane can consist of a few different things. Most commonly, it consists of radials, which are either pieces of wire or piping that come out in a radial pattern at the base of the antenna around the whole base. Otherwise, another ground plane can act as, the metal surface of a car roof. Let's say you have your 2-meter 440 antenna and you mount that on the surface of the car. So the ground plane of that is actually going to be the metal surface of the car. The ground plane ideally extends 1/4 wavelength from the base of the antenna, therefore completing the half wave similar to a dipole. There are other lengths of ground plane antennas. There's the 5/8 wavelength, which is also vertical and more efficient. So it's a little bit longer and more efficient in its nature. It focuses more energy in the horizontal plane, thus it increases range. So what do I mean by that? The energy is actually focused more parallel to the ground, so it can go further instead of going up into the atmosphere. Vertical ground planes are vertically polarized and are also omnidirectional. This is a picture of the typical ground plane vertical antenna. You can see that the main portion of the vertical antenna is here. And then you have these little pipes coming out, aluminum pipes most likely. And these are considered radials, but they can also be considered something called a counterpoise. And this consists of the other half of the antenna, or the ground plane. Okay, let's draw an example of a ground plane antenna. So with this one, let's make a 1/4 wavelength long. And the actual vertical portion of the antenna is here. Forgive me, this should be a straight, nice piece of aluminum, but it's not, because again, I'm not the best artist. So that is your vertical 1/4 wave here. And so you need another 1/4 wave of the antenna to make up the half wave ground plane vertical antenna. So in this case, the green is going to be the ground. Let's say you mounted your vertical antenna on your grass and you attached it to a mast and stabilized it to a piece of concrete. So you're going to lay radials in the grass in a circular pattern or radial pattern going out from the antenna. So these aren't actually sticking up into the air. They're actually in your grass and laying in your grass. You can actually bury these maybe a few inches, and these should radiate in an omnidirectional fashion from your antenna base. And they should all be the same length. And again, ideally, it should be a 1/4 wavelength, similar to the top, to actually create the mirror reflection. So the vertical portion of this is your main antenna. This is what's going to do all the radiation, and these components here are the radials, which comprise the actual ground plane. And for another example, let's just say you have your car as well. Again, not the best artist, but I'm trying. All right, so there's your fancy car. And let's say this is the trunk. And you have your nice vertical antenna, probably with a little bit of a coil on the base. And your car hopefully is metal and not made of plastic or fiberglass. And the trunk and body of the actual car will be the ground plane that completes the other half of your vertical antenna as the mirror image. During the technician exam, you're also going to be required to calculate antenna lengths. And this will come in handy for your ham radio career, because I'm sure you're going to be building antennas and dipoles as your first antenna. So to calculate the antenna length, there are formulas. For a half-wave dipole, you can take the length in feet equals 468 divided by the frequency in megahertz. And that's going to be the length in feet for your half-wave dipole. That's the entire length of your antenna. And if you want to get each length, then just divide that by half. So each component is going to be half that length. Now, if you want to do a quarter wave ground plane vertical and build your own with some aluminum or copper or something else, the length in feet required for that is going to be 234 divided by the frequency in megahertz. And as you can see, that the 468 number, if you divide that by 2, you will get 234, which makes sense since you're going from half wave to quarter wave. And always remember to cut your antenna length long and trim to resonance using your SWR meter or your antenna analyzer, meaning that if you get a value in length in feet in calculating the value for your half-wave dipole or your quarter wave antenna, cut them a little bit longer and then check the SWR and then modify it from there. It's always easy to take some off or trim some off a wire antenna than it is actually adding wire onto your antenna for ideal resonance. And you need to determine your ideal resonance frequency before you do this. Okay, let's actually do some antenna calculations. So let's say you're building a dipole and you'd like it to be resonant on 75, 80 meters. So that's a fairly broad band. Let's say, so we're looking for the 80 meter band, and the band is from 3.5 to 4 megahertz. And what frequency do you actually want to operate on? What point do you want to have the best resonance or ideal resonance? So let's say you want to operate smack dab in the center of the band, and you're going for your general or extra, and you want to set up a nice dipole for that. So let's just say you want to operate at a resonant frequency of 3.75 megahertz. Now, to do this, you can rely on the formula. Remember, you're going to calculate the dipole. So if you remember that formula, the length of your antenna is going to be equal to that magic number of 468 divided by the frequency in megahertz. And the frequency in megahertz that you want is 3.75. So if you do the math, you should come out with a value of 124.8 feet. So that is the length of your entire half-wave dipole antenna. So that's what you're going to cut from end to end and then feed it in the center. If you want to figure out where to feed it in the center, you'll just divide that by 2, which will get you 62.4 feet. So you can have 2 segments or 2 poles of 62.4 feet and attach them to your feed line and come up with a nice dipole antenna. If you don't want to remember that formula or the other formula for a quarter wave antenna or these specific numbers, you can rely on your friend that we learned before, the speed of light. And from the speed of light, you can do multiple calculations. So understanding something, in my opinion, is a little bit better than memorizing equations. So as we recall, this is, let's just break this up. So the first method is up there. And let's do my method. So the speed of light, as we remember, is 300 million meters per second. And the frequency we want is going to be in cycles per second. All right? So to cancel out, you're going to have seconds on the numerator and cycles in the denominator. And the frequency you're looking for is 3,700,000 750 megahertz, or 3.75 megahertz. I'm sorry. So 3,750,000 hertz. So let's write that out. And you can see that the units will cancel. So the seconds will cancel. And you're going to be left with the wavelength in meters. And we can get rid of a lot of these nice zeros as we did in the units lecture to make your math a little bit easier. And that's going to be equivalent to 80 meters. Go figure. So that's what you want, right? So, but now you don't have a metric tape rule. You've got a imperial unit tape rule. So we'll have to go back to that lecture and remember that 80 meters, to convert that to feet, you want to, there's what? So there's 3.28 feet in every meter. And again, the magic of canceling units, the meters cancel, and you're left with feet, and you're resulting a value. Let's see if I can do the math for you here. 262.4 feet. But that's not what we're looking for, right? So that's an entire wavelength. That's one lambda. So this is one lambda, an entire wavelength. But we want the dipole to be half a wavelength long. So we're going to divide that by 2, which will give us a dipole length of 131.2 feet. So the entire dipole length will be 131.2 feet. This is going to be a little bit different than the calculated value up here using the formula of 468 divided by the frequency in megahertz, but this is going to be a lot easier to remember. And this number is a little bit larger, so you can actually utilize this number and then trim it to your SWR or antenna analyzer to achieve optimal resonance. So if you're stuck on the exam and you can't remember what that value was, what the formula was for a half-wave dipole or a quarter-wave dipole, all you need to do is remember what the speed of light is and then do the math and kind of use common sense and figure out the value from there. And you'll have your answer. No memorization required. Your handheld radios, or HTs, also have antennas, and these are known as rubber duck antennas that generally come stock with the radio. This is a ground plane antenna with a coil that will, essentially the coil creates inductive loading, which lengthens the antenna electrically while shortening the physical length of the antenna. So that coil is at the base of the antenna because you can actually see it in the rubber duck. The base of the antenna is typically a little bit thicker than the tip, and that's where the coil is, and that's where the inductive loading occurs to actually physically shorten the distance of the antenna while maintaining a appropriate electrical length for resonance. And the ground plane of the antenna consists of the radio body and also, to a certain degree, the operator itself, or his or herself. Another thing to remember is that rubber duck antennas are less efficient than full-size ground plane antennas, and that should be fairly obvious from our prior discussions. Another tip is to remember to hold your handheld transceiver, or HT, and antenna vertically for proper polarization if you're trying to transmit on voice or FM or narrow FM, because all the repeaters that utilize voice or FM transmission are going to be vertically polarized. So you want to hold your handheld transceiver with the antenna in a vertical fashion to ensure that your polarization matches the other party's polarization or the repeater's polarization. A neat way to actually do this is to maybe tune to the NOAA weather radio or NOAA frequencies, and maybe don't tune to the frequency or station that's directly the closest to your own home location or your current location. Tune to one that's a little bit further away, where you have a little bit of borderline transmission or borderline reception. Hold the radio vertically and then turn it 90 degrees and turn it horizontally. You're going to see and hear that the signal is much more diminished, if not lost. And if you turn it back to a vertical position, that signal will become much stronger. So that's an example of polarization. Another tip, when you're using your HT radio, you can use it inside your vehicle, but if you do that, the signal will be around 10 to 20 times weaker than the signal outside. That's because your car provides some significant shielding, especially if your car or truck is made of metal. So you're essentially within a metal cage that will inhibit reception and inhibit radio transmission. So if you want to get by this, you can either step out of your car while it's stationary, of course, and not moving, and use your HT outside. Or if you have to operate the HT within the car, then mount an external antenna on the trunk using the metal of your car as a ground plane. Directional antennas have more gain than a ideal antenna. So as an omnidirectional antenna, for example, so they don't have more power per se than another antenna. It's the same amount of power, but they're focusing that energy in a specific direction. They're focusing the radio frequency energy in a specific area. It increases signal transmission and reception. And you can actually utilize this to reduce unwanted noise or unwanted signals in the opposite direction. Let's say you want to talk to a station that's north of you, but you're getting a lot of interference from somebody who's directly south of you. If you utilize a vertical or a directional antenna, all you need to do is point your antenna to the north for better reception and better transmission, and there will be a null zone directly in back of you or to the south that will reduce the amount of noise or signal heard from the southern direction. UHF and VHF signals and beam antennas can be used to reflect signal off surfaces to actually get around obstacles. So let's say you have a building that's right in front of you, but you want to talk to your friend that's in the opposite direction or in back of the building. If you have another large structure that's parallel to that object, you can actually turn your directional antenna towards that and kind of do a bank shot off that building, and your signal will be reflected and go into the back of the obstruction, just like you're playing pool. So you're going to reflect your pool ball off the side of the pool table to get to a certain pocket or a certain location. This slide shows examples of different directional antennas, and the antennas that they are showing right here are called the Yagi antennas. The Yagis have, as we learned in previous lectures, they have the driven element, which is actually connected to the coax, and in back of the driven element is the reflector. So that length of wire or tubing reflects the signal from the driven element that's attached to your coax, and it moves it forward into the directors. And directors are known as the components or wires or tubes that are in front of the driven element. So this picture of a Yagi antenna to the left over here is a one that's horizontally polarized. So this is not something you're going to want to use for FM, VHF, and UHF transmission. This is something that you're going to utilize for single sideband or CW transmission, which are generally horizontally polarized signals. And on the right, you're going to see a similar Yagi, but this is vertically oriented or vertically polarized. This you can use for 2-meter VHF, UHF transmission and reception with FM voice, since the repeaters and your fellow station who you may be speaking to have radios and antennas that are vertically polarized. This is a RF diagram of the directional pattern of a Yagi antenna, and you can tell that the signal is transmitted in one direction with nulls off the lateral components and a null to the opposite side. So you're really not going to be hearing people to the side of you or in back of you, but you're going to have most of your gain in the forward direction. So it's taking all that power of the antenna. It's not increasing the power. It's focusing the power. It's focusing it in a directed radiation pattern towards the desired station that you want to communicate with. For UHF and microwave frequencies, it's a little awkward to actually build a Yagi antenna since they're getting smaller and smaller and smaller. But for this, you can use something like a parabolic dish. And this is commonly used in microwave transmission and reception. So this is your preferred method of directed communication at these frequencies. Okay, that's going to wrap up another lecture, and we hope you learned a lot about basic antenna types, including the dipole, ground planes, and you remember how to calculate the antenna length if you want to build your own antenna, and also for the exam by a few different methods. And to cap it off, we did review the directional antennas such as the Yagi and parabolic dishes as well. So thanks again for joining us. And if you feel like supporting us, go to radiosignals.org and click the support button. And don't forget to like us on YouTube and subscribe to our channel. We'll see you next time. Bye. 73.